passing. Hello, hello, hello. Passing रहना. Assalamu alaikum. Alright, so in the previous lecture we started exploring the photoelectric effect. The basic aim was to see that there is a particulate nature of light. We've already seen that light has a wave description as well, because we've seen phenomenon of interference, we've seen the phenomenon of diffraction, and these phenomena could only be explained if we assume that light comprises waves, and these waves interfere. But now we've started to looking at another aspect of light and radiation in general, and that is the particulate existence. So a quick recap of the photoelectric effect and the experimental arrangement which Philip Leonard had for his experiments. So he took a glass bulb. Inside the glass bulb there was an electrode and another electrode, and across this electrode a voltage was applied. One could measure the current with the help of a microammeter or a galvanometer, and one could also apply a voltage, and the voltage was variable. No talking, please. So this is a variable voltage supply, and the voltage can be changed such that this can be made the positive terminal, this supply can be switched so that this can be made the negative terminal. And the voltage was also measured with the help of a voltmeter, V0. And Philip shone light onto this electrode, which passes through a filter F. So this light reaches this particular electrode. The electrode is shaped in a concave form. Electrons are ejected, and if there is a positive potential applied at this electrode, these electrons will be attracted towards the electrode, and they will flow through the circuit. A current will be measured. They will go here, 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 they will flow through the battery, and the circuit will be complete. So what is happening here is that photons are striking this metal, or light is incident upon this metal, and electrons are being ejected, and those electrons are constituting a current. So this is called the photoelectric effect. Now the very interesting observations of Philip Leonard, which he was unable to explain, were the following. If one plotted the voltage V0 or E times V0, which is the energy, with respect to the photocurrent, so the current flowing through this circuit is denoted by small I, and the intensity of the incident light is denoted by a capital I. What does the intensity of light mean? What's the meaning of the word intensity?
The number of electrons that flow as if ejected.
Alright, the number of photons that are incident upon this electrode. It's the brightness of this source, and the intensity can be changed by having a higher wattage bulb, use a bulb of a higher wattage, or moving this bulb further away. That will decrease the intensity, because the intensity is proportional to 1 over r squared. The higher the distance, the smaller will be the intensity. And I gave you the example of stars and the sun. There are stars that are much brighter, much luminous than the sun, but since they are further away, they look dimmer. So Leonard plotted a graph between the photocurrent and the applied voltage. So this is 0 for the voltage, and this is the positive direction of the voltage. which means that this plate is positively charged. When this plate is positively charged and you keep on increasing the voltage, the photocurrent does not change. This is something very strange. You increase the voltage, keep on making it more positive, but the photocurrent does not change. However, if you make the voltage negative, which means that you reverse the polarity of this battery, the current starts to decrease. It bends, and finally, at a certain voltage, at a certain negative voltage, which is called the stopping voltage, Vs. The current diminishes, it goes to zero. Now this is for a certain intensity of light, I1. Now if the experiment is repeated with a different intensity of light, that is if the lamp is brought closer to this tube, a curve is obtained. Of course, when the intensity is higher, it's I2, where I2 is larger than I1. Remember, this is the intensity of the incident light. Okay? I1, capital I1 and capital I2 are the intensities of light. And small I is the current. So higher the intensity, the current is higher. So here the current is higher with respect to this. And when the voltage goes negative again, this current starts decreasing again. And it meets the previous curve at the same value of the stopping voltage. Now this is something very strange. Even though the intensity is higher, one is expecting more electrons, a higher energy being transferred to this electrode. The electrons that are ejected should be of a higher energy. This is the classical perception. अब ये बात गौर से सुने. ये इतना confusing क्यों है? Confusing इसलिए है कि if you increase the intensity of light, you expect classically that more energy is falling onto this electrode. Alright? So when electrons are ejected, they must have a higher energy, a higher kinetic energy. Which means that if that plate, if I am an electron and I am on this electrode and that plate is negatively charged, if I have a higher energy, I can move closer and closer towards the electrode. And if I have enough energy, I can even surpass the repulsive force of that electrode and reach the electrode and make up a current. So if I start off with a higher energy, I have a higher probability that I can reach the electrode and form a current. So the higher intensity would actually give me a more negative stopping voltage, should give me a more negative stopping voltage. Because my expectation is that the electrons that are ejected must have higher energy. So my classical intuition tells me that this curve should actually go like this. A more negative stopping voltage should be required for the higher kinetic energy electrons ejected when the incident light is intense. But I don't see this. I find the same stopping voltage. Alright? Now this cannot be explained by any classical means. The other experiment which Philip performed was the following. He plotted a graph between the maximum kinetic energy. Can you tell me what the maximum kinetic energy would be in terms of the stopping voltage? K max, which is the maximum kinetic energy of the ejected electrons, has to be equal to Vs times E. Okay? So the stopping voltage is a measure of the kinetic energy. Because the stopping voltage is applying a potential difference between these plates. If this plate is negative, then the potential difference between these plates is Vs. and the energy difference between these plates is E times Vs. So this is at a higher potential for the electrons and higher potential with respect to this potential by E times Vs, right? This is a potential energy difference. If the potential is V, the potential energy is E times V. So this is the potential energy barrier which electrons have to surpass in order to reach this electrode. So there are electrons that are being ejected, and all of them do not have the same energy. Some electrons have, if you look at the energy of the electrons that are being ejected, if I plot the energy here of the ejected electrons, and here I plot the number of electrons with a certain energy, and all of this energy, by the way, is kinetic energy. Then there are electrons that are emitted. The curve looks like this. Most of the electrons, the highest number of electrons are emitted with a certain energy, but there are few electrons that are emitted with higher energy. All the electrons will not have the same energy. So this point is the maximum kinetic energy of any electron that is ejected from the surface, and the number is very small. Here the number is smaller. So any electron that has energy, if you apply the stopping voltage, only the electrons that have this much energy, K max, are able to reach the electrode. Any electron that has energy less than K max is not able to reach the electrode, because K max is less than V. K max is equal to Vs E, and the kinetic energy of most electrons is less than Vse. So the stopping voltage is a measure of the maximum kinetic energy, G.
So at the stopping voltage, no electron reaches.
So the current really goes to zero. The current has dropped to zero. G.
Sir, is this graph how negative direction?
It doesn't go in the negative direction, right?
Shouldn't it?
It doesn't go in the negative direction. Alright? So now what? So K max basically is a measure of the stopping voltage, or the stopping voltage is a measure of the maximum kinetic energy. So what Philip Leonard observed, he varied now he used different kinds of filters in between the light bulb and the source and the electrode. अब फिल्टर क्या काम करेगा? फ्रीक्वेंसी को चेंज करेगा. इस लाइट बल्ब के अंदर बहुत सी फ्रीक्वेंसीज थी. हमने लाइट बल्ब का स्पेक्ट्रम भी देखा था किसी डेमोन्स्ट्रेशन में. उसके अंदर बहुत सी फ्रीक्वेंसीज हैं. आप उसके आगे फिल्टर रखें, यू पिक अप ओनली अ पर्टिकुलर फ्रीक्वेंसी और अ पर्टिकुलर वेवलेंथ. सो ही changed the filter in between the bulb and the electrode to pick up a frequency of interest or a wavelength of interest. So he varied the frequency, and he observed a linear relationship between the frequency and the maximum kinetic energy. And this curve was obtained at a constant intensity of light. So if I is kept constant, you increase the frequency, the maximum kinetic energy goes on increasing. Now again this is confusing, because you're not changing the intensity. The amount of light that is reaching the electrode is not changing. It's delivering constant energy to the electrode. This is our classical intuition. But the maximum kinetic energy of the electrons is constantly increasing. Now this is something that cannot be explained classically. And another point is that at a certain frequency f naught, the maximum kinetic energy is zero. So if you're at this frequency f naught, and you're at or you're at frequencies below f naught, you do not observe the kinetic energy is maximum kinetic energy is 0. You do not require any stopping voltage. The stopping voltage is 0, which means no electrons are being ejected. So even if you are at frequencies below f naught, and even if you increase the intensity of the light, the electrons ejected will be none. The maximum kinetic energy will be 0. तो अगर आप frequency f naught से कम frequency इस्तेमाल करते हैं, no matter how large an intensity of light you apply or shine on the electrode, no electrons will be ejected. Now again, this is something very counterintuitive. हम तो ये कहते हैं कि we are shining more light on the electrode, so the electrons should get more energy, and when they get more energy, they should be able to constitute a current. They should have some kinetic energy. But here you are observing the kinetic energy, maximum kinetic energy is 0, which means that the kinetic energy is 0. No electrons are being ejected, even though you increase the intensity of light by a very large amount. Alright? What if you increase the intensity of light? What will this curve look like? This curve does not actually change. Our intuitive prediction is that if you increase the intensity for a given frequency of light, the maximum kinetic energy should be higher. So our intuition suggests a curve like this. This is our classical intuition. Intuition समझते हैं? Intuition का मतलब समझते हैं? Common sense. हर इंसान के अंदर एक intuition होती है किसी चीज की, ठीक है, जिसे कश्फ कहते हैं. कश्फ होता है उसका, उसको कॉमन सेंस होता है, उसको अपनी जिंदगी बचानी है. हर जानवर ने अपनी जिंदगी बचानी है, इसको कहते हैं ज़ौक़ हिफ्ज़ जिंदगी. उसने अपनी जिंदगी बचानी है, वो उसकी इंट्यूशन है. आप उसको सिखाएगा नहीं. हर परिंदे ने उड़ना है, चिड़िया का बच्चा पैदा होगा, उसने उड़ना है, वो उसकी इंट्यूशन है. छोटे बच्चे ने बोलना शुरू करना है उस जुबान में जिसमें वो घर में पलता पड़ता है, वो उसकी इंट्यूशन है. तो हमारी क्लासिकल इंट्यूशन यही कहती है कि इफ यू इंक्रीज द इंटेंसिटी, यू शाइन मोर लाइट onto the electrode, it should give some ejection of electrons. So this is a classically predicted curve. But classically what you see is that the curve does not change at all. Ji.
It doesn't classical intuition also suggest that the curve should begin from the origin? Because
right. The classical intuition also suggests that zero frequency.
Because there's no kinetic energy. If there's a frequency, there should be a kinetic energy.
No, the frequency, this is the frequency of the light. Classical intuition means, now incident light cannot have zero frequency. That just means a DC electric field. So light must have some frequency. You cannot have light of 0 hertz. That's a constant electric field. Light is an electric field. Light एक electric field है, लेकिन उसकी कोई AC field है, वो उसकी कोई frequency है. तो zero frequency light का मतलब दरअसल कुछ नहीं है, वो एक constant electric field है. ठीक है? तो अब इन results को explain करने के लिए हजरत आइंस्टाइन उतरते हैं मैदान में. अब आइंस्टाइन की प्रेडिक्शन जो मैंने जिसका पिछली दफा क्लास में कहा, बड़ी सिंपल क्लियर लॉजिकल आर्गुमेंट्स पर बेस्ड थी. ठीक है, क्लासिकल पिक्चर में इसको आप डिस्क्राइब नहीं कर सकते इन एक्सपेरिमेंटल रिजल्ट्स को. तो आइंस्टाइन ने एक बड़ी स्ट्रेट फॉरवर्ड सी लॉजिकल सिंपल क्लियर आर्गुमेंट्स के जरिए इसकी एक्सप्लेनेशन दी. और उसने क्या कहा, अब जो उसने कहा मैं उसको अपने लफ्जों में आपके सामने पेश करता हूं. Now this electrode, probably Philip used cesium metal. Now this electrode is a metal, so it will have quantized energy levels. Let's not go into details of how these energy levels are found, but we know that these levels are quantized. So this is axis is energy. And there are electrons that fill up these levels. So there are electrons. Suppose I'm putting 2 electrons in each level. All right. Now this energy corresponds to vacuum. When I write vacuum, it means that if an electron has an energy equal to or higher than this energy, it will not belong to the metal. It will be free from the metal. In other words, the electron will have been ejected from the surface of the metal. Just like evaporation, if you have a boiling pan of water, there are molecules inside the liquid, and some of the molecules that have higher energy can break themselves free from the cohesive forces of the other molecules and evaporate. So this is just like evaporation of electrons from a metal. If you provide any electron with energy equal to or higher than this energy, it will be free. It will be ejected. Now this is the topmost field level. The topmost field level. Alright? This is called the Fermi level. And this difference in energy, that is between the Fermi level, which is the topmost field level, and vacuum, is generally denoted by phi and is called the work function. Work function. Now suppose you have a photon. Now this is Einstein's explanation. You have a photon which falls onto the metal surface, and Einstein said that the incoming stream of light is not a classical wave, rather it is a stream of particles. It's not a wave, it's a stream of particles. Particles that are called photons, and each photon has a certain energy. It's a packet of energy. जब हम पार्टिकल का लफ्ज़ इस्तेमाल करते हैं, इसका मतलब पैकेट ऑफ एनर्जी, कैप्सूल ऑफ एनर्जी. ठीक है? तो इस फोटोन के अंदर एनर्जी है HF, and this photon strikes the metal. If this photon has an energy HF that is greater than the work function, then it can give energy to this electron. Alright? When it gives off energy to this electron, the photon disappears. It's annihilated because the rest mass of the photon is 0. And this electron can jump from the Fermi level and go into vacuum. And the extra energy which the electron has, extra energy of the ejected electron, which should be HF minus phi. So when an electron has been ejected, it goes out into vacuum, that is, it is free from the surface of the metal. Now it's inside this glass bulb. It has come out of the metal. This is an electron, an ejected electron called a photoelectron. Now this photoelectron has gone out. It has a certain kinetic energy. It requires a certain kinetic energy, and that kinetic energy is given by the difference of the incident photon's energy and the work function. But when an electron comes out, it sees other electrons. अब देखें, हमारे घर में से अगर कोई फर्द छोड़ के चला जाए, तो वो जब वो खैर बात कहता है, आपने खुदा हाफिज कहता है अपने सारे अहले खाना को कि मैं जा रहा हूँ, तो कोई उसके घर वाले रोते हैं, उसको रोकने की कोशिश करते हैं कि ना जाओ। एक स्कैटरिंग फिनोमेनन होता है, वो कुछ अपनी एनर्जी लूज कर देता है उस प्रोसेस में। ये जब इलेक्ट्रॉन अपना जर्नी ऑफ पार्टीशन तय करेगा तो इट विल lose some of its energy in scattering processes. It will collide with other electrons. It will collide with the ions inside the metal. So there is some scattering that is going on. So not all of the electrons will be ejected. Some of the electrons will not have enough energy after scattering, enabling them to be ejected. मुसाफिर तो बहुत चलते हैं, मंजिल पे पहुंचते हैं 2-1। बहुत से लोग चलते हैं लेकिन मंजिल पे कुछ लोग ही पहुंचते हैं। तो कुछ इलेक्ट्रॉन्स तो अपना सफर यही, अपनी एनर्जी यही एक्सपेंड कर देंगे। ओनली द मोस्ट एनर्जेटिक इलेक्ट्रॉन्स विल बी इजेक्टेड। सो इफ आई टेक दिस डिफरेंस, this will be equal to the maximum kinetic energy of the electrons. Okay? So this is not just the kinetic energy, this is the maximum kinetic energy of the electrons, because this electron which satisfies this equation has not undergone any scattering process. And this of course is equal to VSE. मैं इसको मॉडुलस में इसलिए दिखा रहा हूं, VS कुछ लोग नेगेटिव कहेंगे, कुछ लोग पॉजिटिव कहेंगे. So this is Einstein's photoelectric equation. Now this equation explains, and this reasoning explains everything that we see here. Now if you increase the intensity of light, alright, first of all, if you increase, this is fixed for a certain metal, 3 electron volts, 4 electron volts, 5 electron volts, ये metal की property होती है, work function, ठीक है? H भी आपको पता है constant है. Now if you increase frequency, what's going to happen to the kinetic energy, maximum kinetic? It's going to increase. So there has to be a linear relationship between K and F. So if you look at this curve, F increases, K increases. Alright? Now can you tell me what the value of F naught is going to be? Just raise your hands. Don't speak up. I would like to know what is the value of F naught. आप बताएं, आप में से कोई बताएं. 5. इसको गौर से देख के बताएं कि when the frequency is F naught, what is the maximum kinetic energy? 0. So what is F? Right. So F naught is phi over H. So this value F naught is phi over H. So by looking at the point where the graph starts, you can either find the value of the work function. If H is known, if you know the work function, you can find the value of the Planck's constant. ठीक है? Now what is the slope of this graph? H. So this was one of the first determinations of the value of H. पहली दफा H की वैल्यू, खैर वो तो प्लैंक ने की थी एम्पिरिकल मेथड से, कर्व फिटिंग के जरिए. पहली दफा H की वैल्यू प्लैंक ने फाइंड की थी ब्लैक बॉडी रेडिएशन को देख के. दूसरी दफा प्लैंक्स कांस्टेंट की वैल्यू 1911 में मिलिकन बड़ा टैलेंटेड फिजिसिस्ट था, अमेरिकन फिजिसिस्ट. 1911 में उसने प्लैंक्स कांस्टेंट की वैल्यू फाइंड की थी. लगे आप ये भी ऑन कर दें. अच्छा, तो इसकी स्लोप H के बराबर है. अच्छा, व्हाट इफ वी इंक्रीज द इंटेंसिटी ऑफ द इंसिडेंट लाइट?
The slope stays the same.
what happens in this picture? If you increase the intensity of light, should the maximum kinetic energy of the electrons increase? No, it should not increase, because increasing the intensity means you are shining more photons. Shining more photons, but each photon carries an energy HF. The energy of an individual photon does not increase by increasing the intensity, just that we have more photons. So the intensity has nothing to do with the energy in the quantum picture. The intensity is just the brightness. How many photons are reaching the electrode? And if each one of those photons has an energy less than the work function, none of them can do a photo ejection. Photoelectric effect will not take place. खा जितने मर्जी फोटॉन्स आप बढ़ा दें, खा आप बहुत इंटेंस लेजर ले आए, अगर उसकी फ्रीक्वेंसी प्रॉपर नहीं है, वो f0 से ज्यादा नहीं है, it will not initiate or trigger any photoelectric effect. So increasing the energy, or sorry, increasing the intensity, you increase the intensity, if you increase the intensity, this maximum kinetic energy does not go up. It remains the same, because the energy, kinetic energy, only depends upon the incident frequency. And another thing that we observe is that the photoelectric effect is a 1-to-1 encounter between a photon and an electron. Yani, for example, if the work function is 5 electron volts and you have an incident photon of energy 1 electron volt, will this photon be able to initiate a photoelectric effect? Never. No. However, if you have 5 photons, each with the same energy, 1 electron volt, will it initiate a photoelectric effect? No. Because the photoelectric effect is a one-on-one encounter between an electron and a photon. A photon, many photons cannot bunch up and share their energy. हम गाड़ी को धक्का लगाना चाहते हैं, हम चाहते हैं कि एक बंदे से धक्का नहीं लग रहा, चलो 5 बंदे मिलकर धक्का लगा लेते हैं. ऐसे नहीं होता क्वांटम वर्ल्ड में. क्वांटम वर्ल्ड में एक बंदा ही धक्का लगा सकता है. आपको अगर धक्का लगाना है गाड़ी को, तो आपको एक ही बंदा ताकतवर चाहिए. ये नहीं होगा कि 5 बंदे कमजोर से वो मिलके धक्का लगाएं और उनमें इतनी ताकत आ जाए कि गाड़ी मूव कर जाए. So it's a one-on-one encounter between an electron and a photon. Now we have a fair understanding of this curve. Let's revisit this curve. You increase the intensity, keep the voltage constant. You're increasing the intensity, keeping the voltage constant, the photocurrent is going up. Which means that there are more photons reaching the electrode, more photons, and since each photon is able to initiate a photoelectric effect with a certain efficiency, there will be more electrons ejected. And what is the current? The current is simply the number of electrons times the charge on each electron per unit time. Now this number of electrons ejected will go up if the number of photons goes up. So more photons, which means a more intense beam of light, would result in more electrons ejected. However, remember that those photons must cross the frequency threshold. If you have a large number of photons, but none of them crosses the work function, तो वो photons किसी काम के नहीं. So now with the help of a quantum picture, that is, light is comprised of particles, and each particle carries a momentum hf, and it acts like a bunch of energy, not like a wave. Because in wave, if we consider light to be a wave, a classical wave, we cannot explain this, and neither can we explain this. We need a truly quantum picture or a particle picture of photons in order to describe this. One question. So the explanation of the photoelectric effect necessitates or points towards the graininess of light. कि लाइट जो है वो वेव नहीं है, कंटिन्यूस वेव नहीं है, बल्कि पार्टिकल्स हैं, वो जर्रों पर मुश्तमिल है, ग्रेनी है, ठीक है, पार्टिकल्स हैं. तो क्या ये इलेक्ट्रॉन्स की या मैटर की क्वांटाइजेशन के बारे में भी कुछ कहता है, उसकी डिस्क्रीटनेस के बारे में? यस, कि ये जो मैटर है यानी इलेक्ट्रॉन्स है, ये भी पार्टिकल्स हैं. सो देयर इज अ पार्टिकल टू पार्टिकल कोलिजन व्हिच इज एम्बॉडीड इन दिस इक्वेशन. This is a particle with a certain energy. This is the work function. A particle comes in, it expends or use up some of its energy in overcoming the work function, and another particle is ejected with the residual energy. ठीक है? So it's like a particle to particle collision. Thursday को हम लेक्चर में देखेंगे कि ना सिर्फ इस पार्टिकल की एक एनर्जी है, बल्कि पार्टिकल पिक्चर उसी वक्त कंप्लीट होता है जब एनर्जी भी हो और मोमेंटम भी हो. तो आइंस्टाइन एनर्जी की क्वांटाइजेशन तक रुक गया था, उसने इस पार्टिकल के मोमेंटम के बारे में ज्यादा बात नहीं की. ये फिर और साइंटिस्ट थे, कॉम्पटन खास तौर पे, जिसने पार्टिकल के मोमेंटम, फोटोन के मोमेंटम के बारे में बात की. तो अब मैं आपको एक और इंटरेस्टिंग चीज के बारे में बताना चाह रहा हूं. फोटोइलेक्ट्रिक इफेक्ट की बात खत्म हो गई, ये आप सर्वे से मजीद इसके बारे में पढ़ सकते हैं. मैं आपको एक्स रेज के बारे में बताना चाह रहा हूं. और उससे पहले मेरे पास एक छोटी सी प्रेजेंटेशन है एक्स रेज से मुतालिक. पहले मैं आपको वो दिखाऊंगा. ओहो, ये देखें, एक्सरेज क्वांटाइजेशन भी दिखाती हैं, मैटर की क्वांटाइजेशन भी दिखाती हैं, लाइट की पार्टिकल नेचर्स को भी जाहिर करती हैं. एक्सरेज इज आल्सो अ फॉर्म ऑफ लाइट. हाउ इज इट डिफरेंट फ्रॉम विजिबल लाइट? इट्स एट अ मच हायर फ्रीक्वेंसी, राइट, मच शॉर्टर वेवलेंथ. ठीक है, उसके बाद गामा रेज आती हैं. तो एक्सरेज की छोटी सी हिस्ट्री के बारे में आपको एक दो नोट्स बताना, शेयर करना चाह रहा हूं आपसे. Son, in the meantime, can you turn this on, please? I'll start in 15 minutes with this. So, X-rays were discovered almost accidentally in 1896 by Röntgen. ठीक है, और जब ये X-rays discover हुई तो इनके the nature of these X-rays was extremely strange. They penetrated matter. They were not deflected by electric fields. They weren't deflected by magnetic fields. And since so much was unknown about X-rays, that they could not find a better name for it. They just called it X-rays. X, यानी something they don't know about. और वही नाम, इतना अच्छा नाम है कि it sticks to our scientific literature. तो ये पहली तस्वीर है, ये फॉन्ट सॉरी नहीं आया. दिस इज द फर्स्ट एक्सरे इमेज, और दिस वाज द इमेज ऑफ मिसेस रॉन्जन। मिसेस रॉन्जन के हाथ की ये एक्सरे इमेज है। और जब तमाम साइंसदानों की बेगमात की तरह वो भी इस इमेज से ज़्यादा मुतासिर नहीं हुई। उन्होंने जब ये इमेज देखा, उन्होंने ये कहा कि मियाँ साहब आपने तो मुझे अपनी मौत दिखा दी। I've seen my death through this image। तो इस तस्वीर में आप देख सकते हैं, अच्छा जो रॉन्जन था, he was working with cathode ray tubes। So when an electron strikes an electrode, कैथोड रे ट्यूब में ऐसे ही है ना, मैंने आपको कैथोड रे ट्यूब भी दिखाई है। जब इलेक्ट्रॉन इलेक्ट्रोड से आके टकराता है, इट डीसेलरेट्स, राइट, इट स्टॉप्स, उसको ब्रेकें लगा दी जाती हैं। तो व्हेनेवर अ चार्ज पार्टिकल इज एक्सेलरेटेड और डीसेलरेटेड, इट एमिट्स रेडिएशन, और वो रेडिएशन हाई फ्रीक्वेंसी की रेडिएशन है जिसे एक्स रेज कहते हैं। तो उसके पास एक कैथोड रे ट्यूब थी, उसके पास एक फोटोग्राफिक फिल्म थी, कैमरा भी नया नया इन्वेंट हुआ था, फोटोग्राफिक फिल्म थी, उसके ऊपर एक इमेज बना। उसने देखा देयर आर एक्स रेज, देयर आर इनविजिबल रेज दैट आर बीइंग emitted by the cathode ray tube which have nothing to do with the electrons because they are so far away from the electron tube, and he called them x-rays। और ये उसकी बेगम का बेगम, और उसने उंगली पहनी हुई है, this is gold, x-rays do not penetrate through gold। So this is the first shadowgraph और the first radiograph। और उसके बाद यूं ही ये इमेज छपा 1896 में, देयर वाज अ फ्लरी ऑफ इंटरेस्ट, क्योंकि अब आप कोई चीज ओपेक नहीं रही, यू कैन लुक इनटू ऑब्जेक्ट्स, यू कैन लुक इनटू ह्यूमन बीइंग्स। तो सिर्फ 17 साल बाद इस डिस्कवरी के, रैपिड एक्सेलरेशन देखें साइंस की, टेक्नोलॉजी की, ओनली 17 years about 15 to 17 years after the discovery of X-rays, अमेरिकी सदर रोजवेल्ट को एक गोली लगी। 1912 में ये एक्सरे इमेज लिया गया, वन ऑफ द फर्स्ट एक्सरे इमेजेस। उसमें देखें आपको ये इसका, यू कैन सी द बुलेट, दिस इज द रिब केज, वन ऑफ द ओल्डेस्ट एक्सरे इमेजेस। और उसके बाद आपको पता है कि अब एक्सरेज, जिस तरह ये लेजर है, एक्स रेज भी हमारी रोजमर्रा जिंदगी का हिस्सा बन गए। तो अब इतनी ज्यादा मिस्ट्री इन्वॉल्व थी एक्स रेज के साथ, इतनी ज्यादा मिस्ट्री इन्वॉल्व थी कि लोगों ने दवाइयां बनानी शुरू कर दी कि इट एमिट्स एक्स रेज, जिससे आपका सर का दर्द भी ठीक हो सकता है। A lot of mythical arguments were being associated with X-rays and the magical powers of X-rays. So this is one image of a stamp which of an advertisement which claims that they've made a medicine called Kohler's antidote, and this medicine can emit X-rays which can relieve headaches. Of course, no such medicine was made at that time, but this was their claim. The Federal Drug Agency has not yet been born, I think. But X-rays are used everywhere, in all walks of life, and every person somehow has encountered X-rays with themselves or with their immediate family beings. So this is one image of a kitten, एक बिल्ली है जो मिस्र में ममीफाई हुई थी, इसकी मम्मी बनी हुई है, एक्सरेज के जरिए उसको देखा जा सकता है। एक 65 मिलियन ईयर्स ओल्ड कॉकरोच है जिसके इर्द गिर्द वुड की एक लेयर बन चुकी थी, उसको देखने के लिए एक्सरेज इस्तेमाल की गई, और ये एक्सरेज एक खास बड़ी मशीन से आई जिसे सिंक्रोट्रॉन कहते हैं। दुनिया में 140 के करीब सिंक्रोट्रॉन मशीन है, ये भी पार्टिकल एक्सेलरेटर्स की तरह की मशीनें हैं जो एक्सरेज एमिट करती है, बहुत स्ट्रॉन्ग एक्सरेज, हाई इंटेंसिटी एक्सरेज। एनिमल कॉकरोचेस को देख सकते हैं, फिर आप ब्लैक होल्स को देख सकते हैं। ये एक स्टार है और इसके पास एक छोटा सा ब्लैक होल है, और ये ब्लैक होल की इतनी ज्यादा पुल ऑफ ग्रेविटी है कि इट अट्रैक्ट्स स्टेलर डस्ट एंड इट फॉर्म्स एन एक्रीशन डिस्क, एंड व्हेन दिस चार्ज्ड प्लाज्मा rotates around the black hole, since it is accelerating because of the rotation, it is emitting intense X-ray radiation, and it is this X-ray radiation that tells us that a black hole exists here. So even though the black hole is black, but you can see black holes by looking at the matter around the black hole. It forms an accretion disk which is revolving at extremely high speeds with extremely high frequencies, and those high frequencies correspond to gamma rays. Lekin since everything is moving away from us, those gamma rays, when they reach Earth, they become X-rays because of the Doppler effect. So this is an image of a black hole seen through the Chandra observatory. It's an American satellite, it's an American observatory, and this is of a star called Cygnus 1, and it is believed that there is a black hole close to the star, and this is the image of X-rays. So X-rays have all kinds of uses, but let me tell you something very interesting about X-rays, and then I have a demonstration in the end of the class. First of all, so we have to be very quick here. First of all, how are X-rays produced? I've already mentioned a cathode ray tube. So we have a glass bulb. We have a filament. We have an electrode which has a narrow hole in it, and then we have another electrode. And all of this is evacuated. A very high voltage supply is applied between these electrodes. It's very high, can go up to 100 kilovolts. Now this is a filament, a current flows through the filament, and when current flows through the filament, electrons are ejected as they are in a cathode ray tube. These electrons are being attracted towards this potential. This potential is V naught. So the energy the electrons gain when they reach this electrode is V naught E. Okay? So they are accelerated. They gain a lot of kinetic energy. And when these electrons hit the anode, this electrode, they are suddenly stopped. They decelerate very rapidly. So they have to lose up all of the energy that they've picked up. So when they decelerate, they emit radiation. Whenever a charge accelerates, it emits radiation, electromagnetic radiation. This is how your mobile phone works. There's an antenna in which there is an oscillating charge. An oscillating charge means an accelerating charge, and that is emitting electromagnetic radiation. So this electromagnetic radiation is of a very high frequency because this energy is very high. It's of the order of kilo electron volts. So if you have an electron whose energy is of the order of kilo electron volts and you stop it, all of the energy has to go into the radiation, and that radiation must also have the kilo electron volts of energy. So radiation is emitted and this radiation is called X-rays, and this is called an X-ray tube. Now if I were to plot the wavelength of the emitted radiation and the intensity of the X-rays emitted, so what is this kind of graph called, in which you plot intensity versus wavelength? What is this called? हमने बारहा देखे ऐसे एग्जांपल्स, डेमोज में भी देखे. इसको क्या कहते हैं इस तरह के ग्राफ को, कि जिसमें वेवलेंथ के हिसाब से इंटेंसिटी हो? स्पेक्ट्रम. It's called a spectrum. So the graph looks to first order like this. To first order, approximately looks like this. So it starts off at a certain wavelength, sigma naught, which is called the cutoff wavelength. Now can you calculate what this cutoff wavelength should be, and why is there a cutoff wavelength? Why aren't there any photons emitted with wavelengths less than sigma naught? G. Exactly. Now, no electrons. The maximum energy of the electrons is V naught E. Okay? That's the maximum energy of any of these electrons. So the maximum energy is V naught E. And when this maximum energy electron, which is a particle, it is brought to a complete halt, it is brought to a complete rest, will all of its energy go into the emission of photons? So the maximum energy of any photon that is emitted cannot be greater than V naught E. Okay? क्योंकि एनर्जी ने कंजर्व होना है, एक्स रेज की एनर्जी ने कहीं से आना है और वो एक्स रेज की एनर्जी इलेक्ट्रॉन से आ रही है, तो इलेक्ट्रॉन के पास तो देने के लिए वी नॉट ई है, उससे ज्यादा कुछ दे ही नहीं सकता. तो जो फोटोन की मैक्सिमम एनर्जी है वो वी नॉट ई है. एंड व्हाट इज द एनर्जी ऑफ अ फोटोन? इज एच सी ओवर लैम्डा. सो द वेवलेंथ cannot be less than lambda naught, because if the wavelength is less than lambda naught, it will mean an energy greater than V naught E. But V naught E is the maximum energy of an electron. So this is a cutoff wavelength. And longer wavelengths mean less energies. So the longer wavelengths you get higher intensity. Finally, for very long wavelengths, this curve goes down again, because of long wavelengths means low energy photons, they cannot pass through air, they are absorbed by the air. So this spectrum typically falls down. So this is called, this kind of spectrum is called, there's a German word, Bremsstrahlung, which means breaking radiation. But typically what you observe are, अब बड़े ध्यान से सुने, typically what you observe is that there is a continuous spectrum. On top of this continuous spectrum, you also see sharp lines like this. And these lines, the breaking radiation tells us nothing about quantization. It only tells us that the electron is a particle and the photon is a particle. Electron can give away all of its energy to a photon. But these lines tell us something about quantization. They tell us that the internal energy levels are quantized. So for this we have to look at the mechanism of the production of these lines. These lines are called characteristic X-rays. Now very quickly, how are X-rays produced? From a quantum perspective, you have an atom which has a central nucleus charged plus Ze, and you have orbits, a k orbit, an L orbit, an M orbit, an N orbit, and so on. And there are electrons inside these shells. Now what I'm going to do is I'm going to show you how these characteristic X-rays are produced. Suppose a photon, an X-ray photon comes in and strikes this electron. The photon has some energy hf0, the incident photon. Now if this energy hf0 is greater than the energy that binds this electron to the nucleus, this electron will be ejected it will go out of the atom and a vacancy will be created here, right? Which means the atom has now been excited because there is a vacancy in the lower state. So an electron from a higher orbit can jump down and fill up this gap. And when it jumps down and fills up this gap, a transition takes place from an L shell to a K shell. A photon has to be emitted, okay, in order to conserve energy. Now this is an X-ray photon, and this will have a certain energy which is equal to the energy difference between this shell and this shell. Okay, now since this transition is ending on the K shell, this photon is called a K alpha photon. It is also possible that an electron from the M shell falls and fills this vacancy. Then a photon will be emitted. This is called a K beta transition. It's also possible that an electron from the N shell falls here and a photon is emitted. This is called a K gamma photon. You can also have this incident photon striking off an electron from the L shell. So this electron goes out and a electron from the M shell takes its place and emits a photon. This is called an L alpha photon. You can have an L beta photon and so on. So the X-rays that are emitted, they tell us what the energy difference between the inner shells are. And they will have precise frequencies corresponding to these energy differences. And these are called characteristic X-rays. Now very quickly, suppose you have a K shell and an L shell, and an electron falls down from the L shell to the K shell. अब बात को बड़े ध्यान से सुनने, बात नहीं करनी, we don't have much time. Electron falls down from the L shell to the K shell, a photon is emitted, right? Now what's the energy of the electron in the K shell? It's minus 13.6 over n square z squared electron volts. This is the energy in the nth shell. Okay, assuming that the Bohr's model for hydrogen applies to these complicated systems as well. So for the K shell n equals 1, for the L shell n equals 2. So you can find the energy difference. Suppose the K alpha photon is emitted. What is the energy of the K alpha photon? It's going to be this energy minus this energy. It's going to be minus 13.6 z square over 1 over 4 minus 1 over 1. Right? This is going to be 3 over 4 into 13.6 z squared. Alright, so now let's look at a demonstration. Can you please? Now we're going to take 10 minutes extra, 5 minutes extra, so please be a little bit patient. I have to do the demo, so we'll actually do it later. Is everything on? Ready to go? Okay. अहमद जरा थोड़ा सा करीब ले आओ, ऊपर से इसको दिखा दो. प्लीज बी पेशेंट. ये अपॉर्चुनिटी शायद आपको फिर ना मिले देखने की एक्सरेज. यू कांट सी एक्सरेज बट Alright, so first of all, I request you to be patient. We'll take 5 minutes extra. So what we have here is an X-ray system. Now this is an X-ray tube, similar to a tube like this, although much more sophisticated. It is producing X-rays. These X-rays are coming out of this tube, and this is a box, which is a shielded box made up of brass. If I open the lid of this box, inside the box, here I have placed a sample which is of steel. So the X-rays come in, they strike the steel and they go out. And when they go out, they go into this detector. This detector is measuring the energy of the emitted X-ray photons. This process is called X-ray fluorescence. What I've shown on the blackboard is also X-ray fluorescence. So I'm shining photons onto a material. That material is emitting certain radiation, and that radiation will have a curve like this. It will emit Bremsstrahlung. It will also emit the characteristic X-rays corresponding to the elements present inside the material. So this is a small X-ray fluorescence unit. And I would also like you to point your attention towards this sign. This is very important. Whenever you perform an experiment or a demonstration, you have to take into account the safety features of this experiment. I also like to point your attention towards, there are certain rules for doing an experiment, and you cannot expose yourself to X-ray radiation because it's harmful. So that is why everything is placed inside. The X-rays do not travel through air. They travel through inside this box, which has brass and aluminum in it. So there is minimum exposure, and I am wearing gloves because I do not want to touch the X-ray tube. It's very high voltage. If I touch the windows of the tube, it will damage. Now what I'm going to do, I'm going to run a spectrum. I'm going to turn on the X-ray tube, and I would like to see what the characteristic X-rays look like. और देखो, मुझे एक बात बताओ कि ये आपको एक्सप्रेशन नजर आ रहा है ना? By looking at the energies of the emitted rays, it's directly proportional to the atomic number squared. तो ये दूसरा नोबेल प्राइज विनिंग एक्सपेरिमेंट है जो 1913 में मॉजले ने किया था, जिसमें उसने एटॉमिक नंबर्स डिस्कवर किए थे. मॉजले बहुत ही छोटी उम्र में, 27 साल की उम्र में, एक एक्सीडेंट में फर्स्ट वर्ल्ड वॉर में खुदा को प्यार हो गया. ठीक है, पता नहीं कि वो ज्यादा जीता तो क्या क्या डिस्कवरीज करता. तो पीरियोडिक टेबल मॉजलेस का और इस एक्सपेरिमेंट का मरहूने मिन्नत है. ये दूसरा नोबेल प्राइज विनिंग एक्सपेरिमेंट है जो मैंने आपको दिखा रहा हूं. ऑल राइट, सो we have a software that looks at the spectrum. So I would like to clear this first. The X-ray tube is off. There is no high voltage. So I'm going to turn on the X-ray tube. I check whether everything is shielded. Nothing is uncovered. All right, fine. This is the controller for the X-ray tube. I change the anode voltage to 30 kilovolts and the current to 15 microamps. Son, is that fine?
You can use
30 microamps. So 30 microamps is the filament current. So अच्छा, मुझे तो ये फिलामेंट करंट है, ये एक्सरेज की एनर्जी को चेंज करेगा? नहीं, ये सिर्फ एक्सरेज के फ्लक्स को चेंज करेगा. हाउ मेनी एक्सरे फोटॉन्स डू यू हैव? Because this is just the current flowing through the filament. It tells you how many electrons you have, and it also tells you how many X-ray photons are emitted from the tube. The anode voltage, this voltage, is this voltage. This tells us the energy of the X-rays that are emitted. So remember, there's always a difference between intensity and energy. So I'm going to start this. Start MTech Mini X. Alright. Now I'm going to turn on the high voltage supply. Okay? And I'm going to look at the spectrum. Turn on. Since it's very high voltage, it asks me again, क्या वाकई करना चाह रहे हो? Alright, I've turned off the supply and I've obtained this spectrum. Alright, now here what you observe are these distinct peaks. 1, 2, 3, 4, 5, 6, 7, 8 upon a background. This scale is energy. Right? It's not wavelength. आप wavelength भी plot कर सकते हैं, energy भी plot कर सकते हैं. Blackboard पे मैंने wavelength के हिसाब से बताया और यहाँ पे मैंने energy के हिसाब से बताया. ठीक है? तो आप देखें मेरे पास एनोड वोल्टेज था 30 kilovolts. So this spectrum is almost going up to 30 kilovolts. This is 30 here. This is 29 kilovolts, kilo electron volts. This is 30 kilo electron volts. So there are no photons that are emitted with energies higher than 30 kilo electron volts. This corresponds to the cutoff wavelength. There is a cutoff energy as well, which is just hc over lambda naught. And now I've seen these characteristic peaks. Now I would like to identify which elements are these peaks coming from, right? And what are their energies, and what do they correspond to? What atomic numbers do they correspond to? So there is a small exercise I would like to do. I define and I edit a region of interest. I just mark my peaks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, so I've marked my peaks. Now I want to see what do these peaks correspond to. Analyze. I load a library, X-ray K alpha 1, and then I look at my ROI details. Alright, so here you देखिए, there's a K alpha peak from chromium with energy 5.4 kilo electron volts. There is a K alpha peak from manganese, energy 5.92 kilo electron volts. From iron, 6.39 kilo electron volts. From cobalt, 7.04. From nickel, 7.47. Copper, 8.21. Molybdenum, 17.46 kilo electron volts. Alright, now I would like to go to the blackboard and do a little bit some calculations for you and see if it all makes sense. देखें, आप इसको realize करें कि in 15 minutes we're going to see what's inside an atom, and we're going to look at fluorescence from an atom. We're looking at X-rays that are emitted from an atom. First of all, I would like to see that you have chromium, a K alpha peak from chromium, and its energy is 5.4 kilo electron volts. 5.4 kilo electron volts. The atomic number of chromium is 24. Alright, I have it on my notebook as well. The atomic number of chromium is 24. So energy 5.4 kilo electron volts. So my formula for the energy is this. Suppose this is an unknown. Suppose this is an unknown, right? So my 5.4 kilo electron volts energy has to be equal to 3.4 into my unknown, which is E naught, into Z square, which is 24. Since this is in electron volts, I would like to put this in electron volts as well. So I write 5.4 into 1000, which is 5400. So my E naught is 5400 from the experiment. 5400 into 4 divided by 3 into 24 squared. Can you tell me what the result of this calculation is, please? 12.5. What do I expect? I expect 13.6. This is coming from the Bohr's model. Alright? So my experimental result matches somewhat what I expect from the Bohr's model. Now if I replace this 24 by 23, what do I get? If I were to replace this 24 with the 23, what should I get? Right. So if this were 23, I would have 23 here, 23 squared, I would get 13.6. This exactly matches the Bohr's prediction. So instead of 24, I am using 23. Now, is that justifiable? Why? No, that's not experimental error.
So the effective
Exactly, effective nuclear charge. So there is an electron here. There are electrons in the L shell, and there are 2 electrons in the K shell. Now if a photon has struck this atom, this green electron has gone out because of the photoelectric effect. This green electron has been ejected. Now there is only 1 electron in the K shell that remains, and the electrons that are in the L shell, if this electron were not there in the K shell, अगर K shell में कोई electron ना होता, तो ये जो L shell वाले electrons एक charge देख रहे हैं plus Z, जो protons की तादाद है in the nucleus, और वो positively charged है. लेकिन K shell में एक electron बेचारा बच गया है और वो negatively charged है. तो अब मैं एक L shell का electron और nucleus को मैं देख रहा हूँ, मुझे 24 पॉजिटिव चार्जेस नजर नहीं आ रहे, मुझे 23 पॉजिटिव चार्जेस नजर आ रहे हैं, क्योंकि एक इलेक्ट्रॉन है दरमियान में, वो नेगेटिवली चार्ज्ड है. तो आई एम सीइंग एन इफेक्टिव न्यूक्लियर चार्ज ऑफ 23 प्रोटॉन्स. दिस इलेक्ट्रॉन इज स्क्रीनिंग द इफेक्ट of the protons. So my effective nuclear charge reduces from 24 to 23, and I get exactly the same result as predicted by the Bohr's model. Now we've done an experiment, we've looked at X-rays, and we've seen that the quantum mechanics is not something that is there in textbooks. It can be seen. This is how the history of science developed. The last thing, if you look at all of these energies, and you take the atomic numbers of these elements, you plot a graph between the energy and Z squared, it's going to be a straight line. We don't have time to show this, but I can give this to you as a homework after the midterms or something. So this is Moseley's law, and I've given you another example that shows that photons exist, they have precise energies, they act like particles, and that matter is quantized. Thank you very much.